Dear students, now let's solve some of the questions from diffraction. Let's take up the first question. Which property of light is confirmed by diffraction? Options: A. Wave nature, B. Transverse wave nature, C. Longitudinal wave nature, and D. Quantum nature. Dear student, it's a very fundamental question. That is, diffraction is a wave phenomena, and when you have diffraction experiment, it clearly confirms the wave nature of light. However, it doesn't give you any information regarding the nature of the wave because both longitudinal and transverse wave undergo diffraction. However, polarization is the sure test for determination of the nature of wave because only transverse waves undergo polarization but not the longitudinal waves. So, when it comes to diffraction, you can only confirm the wave nature of light but not the nature of the wave. Therefore, option A is the correct answer, that is wave nature of light. Let's have a look at the next question, dear students. The interference differs from diffraction in that options: A. It cannot be observed with white light. B. Unlike diffraction, the interference fringes are of varying intensity. C. Interference minima are perfectly dark and that of diffraction may not be dark. D. The diffraction fringes are of equal width but interference fringes are of unequal width. So now let's select those wrong statements and we'll eliminate them first, and we'll just try to correct those wrong statements also while getting the correct answer. Now look at option A. It cannot be observed with white light. It's a wrong statement because we know that both interference and diffraction can be carried out using white light. So A cannot be the correct answer. Have a look at B. Unlike diffraction, the interference fringes are of varying intensity. It's a wrong statement because we know that interference fringes are of equal intensity, but diffraction fringes or bands are of varying intensities. So B is not written clearly. Look at C. Interference minima are perfectly dark and that of diffraction may not be dark. This is a correct statement because in interference experiment you can see darks whose intensity is perfectly zero, whereas in diffraction bands no minima is completely dark. Therefore C must be the correct answer. However, have a look at option D. The diffraction fringes are of equal width but interference fringes are of unequal width. Again, the statement is incorrect because the interference fringes are of equal width. However, diffraction bands are of unequal width. Therefore, option D is again a wrong statement. So A, B and D are the wrong statements. There is only one correct statement given, that is option C. Therefore, option C is the correct answer. Let's go to the next question, dear students. In a single slit diffraction experiment, the width of the slit is made double its original width. Then the central maximum of the diffraction pattern will become options: A. Narrower and fainter, B. Narrower and brighter, C. Broader and fainter, and D. Broader and brighter. Now, this is the question on the central maximum. We have an idea of the width of the central maximum, which is given by W is equal to 2 lambda divided by D or A. Here D indicates the slit width or the width of the single slit. Now, what is asked is when you increase the slit width to double the initial value, let me make it D equal to 2D or D dash equal to 2D, then I'll get new central maximum, that is width of the new central maximum becomes equal to 2 lambda divided by 2D. That is the half of the original value. So what does it mean is the width of the central maximum decreases. Therefore, it should be narrower. So you can easily eliminate option C and D. It becomes narrower. But now the question is, does it become brighter or fainter? So that depends on the intensity of the central maximum. You know that intensity at any point on the screen depends on the amplitude of the incident light. Here, when you increase the slit width, the amplitude of the incident light increases. When the slit width is increased to twice the original value, then amplitude also increases to twice. That is, the amplitude gets doubled. When amplitude gets doubled, the intensity becomes 4 times. Since intensity is directly proportional to amplitude square, when amplitude is doubled, intensity becomes 4 times. Therefore, the central maximum should occupy. Therefore, more light should be concentrated on the central maximum, or in other words, there should be more light to be seen at the central maximum. Simply, it becomes narrower and brighter. So it has to be more bright than before, since more intensity is reached at the central maximum. It becomes narrower and brighter, therefore option B is the correct answer. Let's take up the next question in diffraction. Consider Fraunhofer diffraction pattern obtained with a single slit at normal incidence. At the angular position of first diffraction minimum, the phase difference between the wavelets from the opposite edges of the slit is options A pi by 4, B pi by 2, C pi, and D 2 pi. Dear students, we know that in order to get a minimum in Fraunhofer single slit diffraction experiment, the phase difference between the two edges of the slit should be equal to phi is equal to 2n pi. This is the condition for secondary minima or minimum. Now, in order to get first secondary minimum, for first minimum, the value of n should be equal to 1. Therefore, phase difference is 2 pi. Therefore, option D is the correct answer. Now let's take some more question on Fraunhofer single slit diffraction experiment. A beam of light of wavelength 600 nanometer from a source falls on single slit 1 millimeter wide, and the resulting diffraction pattern is observed on a screen 2 meters away. The distance between the first dark fringes on either sides of the central bright fringe is options A 2.4 cm, B 2.4 mm, C 1.2 cm, and D 1.2 mm. Dear students, first let's write down the data given. The wavelength of the incident light is 600 nanometer, otherwise it is 6 into 10 power minus 7 meter. The slit width, you can write it as small d or small a, that's equal to 1 millimeter, 1 into 10 power minus 3 meter, and the screen is at a distance of 2 meter, which is given a symbol capital D. Now, what is to be found out is the distance between the first minimum on either sides of the central maximum. When you have a look at the fringe pattern in Fraunhofer single slit experiment, you'll come to know that the distance between the first minima on either sides is nothing but the linear width of central maximum. Or in other words, it is simply the width of central maximum given by the formula W is equal to 2 lambda D divided by D, where small d is the slit width. Now, let's substitute the values known. W is equal to 2 into wavelength is 6 into 10 power minus 7 into the screen's distance is 2 meter divided by small d is just 10 power minus 3. So in numerator you have 4 into 6 is 24. 24 into 10 power minus 4. So 24 into 10 power minus 4 in meter. So you can express this in millimeter. That is 2.4 millimeter. So the width of the central maximum is 2.4 millimeter, and that is the distance between the first minima on either sides of central maximum. Therefore, option B is the correct answer. Now let's take up the next question, dear students. A single slit Fraunhofer diffraction pattern is formed with white light. For what wavelength of light the third secondary maximum in the diffraction pattern coincides with the second secondary maximum in the pattern for red light of wavelength 6500 angstrom? Options: A. 4400 angstrom, B. 4100 angstrom, C. 4642.8 angstrom, and D. 9100 angstroms. Dear students, here two different fringes do coincide, and these two fringe patterns are due to two different wavelengths. One of them is due to white light and the other one is due to a monochromatic light, which is red light. Now, what do we understand by the statement that two fringes do overlap or coincide at a point on the screen? It means that the distance of those two fringes from the center should remain the same. So when two fringes coincide at a point on the screen, then we'll have to equate their distances from the center. Here, what coincides with what? A bright fringe coincides with another bright fringe. So we'll have to equate the distance of bright due to white light of unknown wavelength with that of the distance of. So now we'll have to equate the distance of a fringe due to white light with that due to red light. So we know that the distance of secondary maximum from the center of the fringe pattern is given by, let me write it as distance of secondary maxima it is given by xn is equal to 2n plus 1 lambda d divided by 2d. Now, for third secondary maximum, the value of n is 3. So, by substituting n 3, we get x is equal to 2 into 3 plus 1 is 7 lambda d by 2d. So, let me call this as x1, that is the distance due to the wavelength lambda, and this lambda is unknown, and this is equal to 7 lambda d divided by 2d. Now let me find out the distance of second secondary maximum due to another wavelength, that is of red color. Using the same formula, since it is again secondary maxima, the same formula is valid, but this time it is second secondary maxima. The value of n is 2. Therefore, the distance, let me write it as x2. In place of n, when you substitute 2, you'll get 5 lambda d divided by 2d. But here, the wavelength is lambda r. That is for red color. And that is given to you. Okay? When they coincide, these two distances can be equated. That is, when they coincide, x1 is equal to x2, that is 7 lambda d divided by 2d is equal to 5 lambda r into d divided by 2d. Since the slit width remains the same and the distance of the screen from the slit remains the same, you can cancel them. This d gets cancelled with this d, and small d also gets cancelled along with this 2. So we are left with 7 lambda is equal to 5 lambda r. Anyhow, wavelength of red is known. To find out this lambda, it is 5 by 7 times wavelength of red is given to be 6500 angstrom, or 6.5 into 10 power minus 7. So this is nothing but 32.5 divided by 7 should be slightly greater than 4600 in angstrom unit, and there is only one option which is close to 4600 angstrom, and that is option C, which is 4642.8 angstrom. Therefore, your option C is the correct answer. Let's go to the next question, dear students. In a Fraunhofer diffraction experiment at a single slit using a light of wavelength 400 nanometer, the first minimum is formed at an angle of 30 degree. The direction of the first secondary maximum is options A, sine inverse of 2 by 3, B, sine inverse of 3 by 4, C, sine inverse of 1 by 4, and D, tan inverse of 2 by 3. Dear students, this is a problem based on the angular position of secondary maxima and secondary minima. We'll have to first remember the formulae for these angular positions of secondary maxima and secondary minima. Let's write the formula first. For secondary minima, the angular position is in Fraunhofer diffraction pattern. The secondary minima are situated at different angles, and these angles are given by the formula sine theta is equal to n lambda divided by d, or theta is equal to sine inverse of n lambda divided by d, where d is the slit width. Similarly, for secondary maxima, the angular position is defined as sine theta is equal to 2n plus 1 lambda divided by 2d. Now, have a careful look at these two expressions, dear students. When you want to have an expressions for secondary maxima, when you remember the expression for secondary minima, where there is n lambda divided by d, in place of n, if you replace n by 2n plus 1 by 2, you'll get an expression for the angular position for secondary maxima. Similarly, when you want to write an expression for distance of minima or maxima from the center, I think this angular position formula will help you. When you multiply this angular position formula with capital D, which is the distance of the screen, then that gives you the formula for distance of any fringe from the center. For example, the distance of nth secondary minima is just x is equal to n lambda d divided by d. So I have just multiplied the capital D to the numerator. Similarly, for secondary maxima, the distance can be obtained by just multiplying capital D. That is, distance of secondary maxima from the center is given by x is equal to 2n plus 1 lambda d divided by 2d. Now we'll have to deal only with the angular positions for this problem. For the secondary minimum, the angular position is sine theta is equal to n lambda divided by d, or theta is equal to sine inverse of n lambda divided by d. But you're talking about first secondary minimum. For first secondary minimum, the value of n is just 1. So you'll get an expression for sine theta, that is sine theta is equal to simply lambda divided by d. However, this angular position theta is given to be 30 degree. Therefore, lambda by d is sine 30, that is nothing but half. So I got an expression for lambda by d. Now, I'll go to secondary maxima. For first secondary maxima, for first secondary maximum, the value of n is again 1. So let me call this angle as sine theta dash. So I'll call this as theta dash. Therefore, sine theta dash is equal to, in place of n, when you substitute 1, you'll get 3 lambda divided by 2d. Therefore, sine theta dash is equal to 3 by 2 times what is lambda d? What is lambda by d? Which is already found to be half. So this has to be multiplied by half. that gives you 3 by 4. So the value of sine theta dash is 3 by 4. So you'll find the value of theta dash, which is sine inverse of 3 by 4. This is the angular position of the first secondary maxima in the given experimental apparatus. Therefore, option B is the correct answer.